Things going all right? Good to go on to new stuff then? All right. Well, let's actually get started in earnest in some trig stuff. So we're going to do some trigonometry of right triangles. This is how we're going to introduce where the trig functions come from, and then we'll extend it to all possible angles, not just ones that are in a right triangle, but we'll still use the right triangle ideas to help us as we go along. And then we'll develop our trigonometry analysis stuff from there. All right. So let's just start with what the 6 trig functions are. To do that, let's just set some definitions in our triangle. So first and foremost, what I have here is a right triangle. So this angle right here is 90 degrees. In particular, no matter what angle I'm talking about, what other angle in the triangle that I'm talking about at this point, they will be acute angles. All right, they'll be less than 90 and bigger than 0. Here you go. Sorry, appreciate it. Yep. All right. Pardon me. All right, so let's go through here and set, like I said, I want to set some definitions before we go on. So this is the angle that I'm interested in, this theta that I have labeled here. Small Greek letters are pretty typical for labeling angles. Usually we'll use theta to start, but you'll also see alpha, beta, and gamma used every once in a while. But if you see a theta, it's probably referring to an angle. All right, so these definitions that I have listed here on this triangle are relative to where I've placed that angle. Okay? In particular, if I look at this angle, these two things would be flip-flopped. All right? So when I have this angle here, one of the sides is made up by the hypotenuse of the right triangle. The other one is made up by a leg of that right triangle. So the leg that makes up the angle we refer to as the adjacent side for that angle. Okay? Then the other leg of the right triangle that doesn't touch that angle, that's the one we refer to as the opposite side. Okay? So using that language, we're going to define 6 different ratios out of that triangle, and that's going to give us the 6 different trig functions. Okay? So the first one we're going to talk about is the sine function. So sine has an extra E on the end, but when we do sine function, we abbreviate it S-I-N. Okay? Now these are functions. Okay? Functions, remember, require an input and give you an output. In particular, they require an input. Writing S-I-N and no input makes me think you're in church. Okay? All right? You have to take the sine of something. All right? S-I-N written all by itself doesn't make any sense. Okay? It would make as much sense as writing that with nothing underneath it. Would you ever write a square root symbol with nothing underneath it? No. So then never write a sine function with nothing inside of it. The function, it requires something to go in it. Okay? All right. So the way we define the sine function in terms of the right triangle, you do the ratio of the length of the opposite side over the length of the hypotenuse. And we'll go through and figure out the different functions using the triangle that I have at the bottom of the page. So I just want to get what the definitions are. So that's how we do the sine function. We do opposite over hypotenuse. That's how we get that ratio. The cosine function, we abbreviate cosine as COS. It's the using the other leg but keeping the hypotenuse. So this is the adjacent over the hypotenuse. The third one we refer to as the tangent. It's tan of theta, and it's opposite over adjacent. If I could spell the word adjacent, that would also be helpful. And if you look at your calculator, you'll see buttons for those three. Okay? We have three other ones, but you'll actually see buttons for those three ones, those three in particular on your calculator. They're used enough that you'll want a button for each of them. Okay? That's why they're on there. To give a little bit of it, why we call this particular one the tangent. If you have I'm going to draw this picture here for a second. If you have a circle and I have a radius of 1, and I make a right triangle where I take the segment that comes down tangent to the circle. Remember if you remember your geometry, if you have a circle and a line that's tangent to it, it touches in one spot, that forms a right angle. If this is my theta, the length of this side is tangent of theta. That's where the word tangent comes from. It comes from the word that we use for tangent lines. Just let you know where the names come from. Sine comes from the name for bosom, by the way. This is the way the graph looks, but that's another story for a different day. Okay. So anyway, tangent, that's where that comes from. There's also the hypotenuse of that right triangle is going to pop up here in a second as well. Anyway, let's do the other three. The other three we can think of actually in terms of these functions, but we also have cotangent of theta. So it's tangent with a co in front of it. It's adjacent over the opposite. We have secant, which is hypotenuse over adjacent. And finally, we have cosecant, which is abbreviated CSC. You can't abbreviate cosecant COS because we already have that for cosine. So I have to do something different. And this is hypotenuse over the opposite. So those are the 6 trig functions of that particular angle. I said that the secant comes along also from this picture. Remember, a tangent line for a circle is that line that comes and just touches it in one spot. A secant line for a circle hits it in 2. The length of this hypotenuse in this picture is the secant of the angle. That's where the secant name comes from. Just to relate it to the pictures for circles. All right. We'll come back and look at some various relationships between these things in a little bit. But let's talk about the fact that we have functions. All right? When we have functions, if I put one thing in, how many things am I allowed to get out and keep it a function? Just one, right? You might be asking, well, what happens if I change the size of my triangle? Right? If I change the size of the triangle, that angle could stay the same, but my opposite, adjacent, and hypotenuse could all be different. Right? So how do I know I only get one thing out? Right? That's what I'm asking about with this question, is how do I know I get one thing out? Well, remember back from geometry, if I keep the two angles the same, the triangle is similar. We have similar triangles no matter what, right? I can make it bigger and smaller, but if I keep this angle being a right angle and that being the same theta, I get a similar right triangle. If you think about your pictures maybe I think about this in terms of this particular picture. I have a smaller triangle similar to a bigger triangle there, right? And remember that for similar triangles, those corresponding ratios are the same. So if I had, say, A and B here, and I had C and D here, if they're similar, then I know that A over B is the same thing as C over D. And I still would have opposite over adjacent, right? So you get the same ratio. So when that triangle gets bigger or smaller, well, the triangles are similar. So the ratios don't change. And that's important. I cannot put one thing into a function and get two things out, right? So if I'm going to define it this way, then I better make sure that my ratios don't change. And they don't because we have similar triangles. So that's an important thing. That's the reason why I'm emphasizing that now. It's important for functions. One thing goes in, one thing comes out. Right. So let's see if we can answer some questions using these definitions. So I have a right triangle. I didn't mark it because I was lazy when I drew the pictures. But in this section, everything we have is a right triangle. This right angle is going to be here. It asks you to find the 6 trig functions of theta. What sides are we given for this particular theta in this case? Opposite and the hypotenuse, right? So right away, which one can we find pretty quickly? The sine, right? Your sine of theta will be 5 over 13, the opposite over the hypotenuse. Everybody okay with that? But to do, say, cosine, I need to know what? The adjacent side, the one that's missing. Any famous theorem you might know to help you figure out that missing side? Yeah, you have the a squared plus b squared equals c squared. The Pythagorean theorem, exactly right. So maybe I call this one b. It doesn't matter if you call it a or b. I don't really care. If I call it b, what's the equation we would have? Yeah, so if we do it'd be 5 squared plus b squared equals 13 squared, right? 25 plus b squared equals 169. B squared is 144. So b is 12. Good. Now that I have that adjacent side, I think I'm good to go with all of them now, right? Cosine of theta is going to be what? Over 13. Tangent of theta is going to be 5 over 12. Move stuff out of the way. Cotangent of theta will be 12 over 5. Secant of theta will be 13 over 12. And cosecant will be 13 over 5. Good. Again, we're just using the definitions that we came up with for the six different trig functions. Are there any questions where those numbers are coming from? You notice some relationships between some of these. Like, for example, do you notice a relationship between the tangent and the cotangent? Yeah. They are. Okay, inverses are good. Reciprocal, right? They're flipped upside down. Yeah, I knew what you meant. I just want to get the right word in there. So they're reciprocals of each other, right? And we can notice that just from generally looking at the way those two things are defined, right? It's literally just flipped upside down, isn't it? Do you see any other reciprocal relationships? Yeah, secant and cosine are reciprocals of each other. Yeah, the sine and the cosecant are reciprocals of each other. Okay. And that's true in general. See if you can work on the second one there, and then we'll chat about it, where it's asking you to construct a triangle and then figure out what the other 5 trig functions of alpha are. I used an alpha there instead of a theta. Ready to chat about this one? Okay. So the way I would attack this is draw a picture. Draw a right triangle. Start there. Okay. So right triangle here, alpha here. They tell you that the tangent of alpha is 9 over 4. So relative to where I put that alpha, what can we label for sides here? Yeah, the opposite and the adjacent, right? Tangent is opposite over adjacent. So I could label the opposite side as 9 and the adjacent side as 4. Can I figure out the hypotenuse? Yeah. Same way we did the other, figuring out the leg earlier, right? Use Pythagorean theorem. Okay. So if I have 4 squared plus 9 squared equals c squared, what? 4 squared is 16, 9 squared is 81, 97 is c squared. So c is square root of 97, and I don't see any perfect squares in there. So square root of 97 is about as good as I can get. I certainly do not expect you to change it to a decimal. Okay. All right. But now that we know what c is, can we figure out the other 5 functions? Yeah. What's sine of alpha going to be? Yeah, the opposite over the hypotenuse, so 9 over the square root of 97. Do you think I give a rip if you rationalize that denominator? No, I do not care. Do not waste time rationalizing the denominator. Okay. I know that in high school, some teachers will emphasize the heck out of rationalizing a denominator. Okay. Rationalize that denominator. I challenge you. Spoiler alert, can't get pi out of the denominator, so it can't be rationalized. Okay. Don't care. You can leave the square root of the denominator. We are all big boys and girls. We can handle square roots of denominators. Okay? The fact of rationalizing a denominator, not a big deal. The process of what you do to rationalize, that's important later. Okay? But as far as actually getting a square root out of the denominator, please, please, please do not waste your time. Okay? If you care that much, you're just going to type it in a calculator anyway and get a decimal approximation. Okay? All right. Sorry, I know I went on a rant. It's fine. I've seen so many students get into my classes and can't do anything else, but they can rationalize a denominator. So not important. All right, anyway, cosine of alpha. Yeah, 4 over square root of 97. We already have tangent of alpha because that was what we were given. So cotangent of alpha is, yes, is the reciprocal of the tangent, right? The 4 over 9, adjacent over opposite, right? Secant is square root of 97 over 4. Cosecant. Yeah, good. Square root of 97 over 9. Good. That one okay? Yes. Secant is the reciprocal of cosine. Exactly right. Yep. You can just take your cosine and flip it upside down. Exactly right. This one all right? All right. So going forward, there'll be some special angles that will want to know what the exact values of the trig functions are. So this is going to require us to remember a little bit, of geometry stuff. Okay. Let's actually do the one on the right first. Let's do what we refer to as a 45, 45, 90 triangle. So again, the right angle is here. If I know that these two angles are the same, what do I know about the two sides? They're also the same, right? So this also has to be a 1, right? And now can you figure out the third side? Yeah, the Pythagorean theorem again, right? 1 squared plus 1 squared would be the hypotenuse squared, so I end up with square root of 2 here. So now we can use that triangle to help us figure out the trig functions of 45 degrees, right? Okay. So that one was a little bit, and we're going to fill out the table here in a second. That was a little bit easier to figure out, right? That wasn't too bad. I had an isosceles triangle to start with. I know it was isosceles because my base angles there were equal. So if the two base angles are equal, the two sides are equal, then I can figure out the third. It's the right triangle. All right. The other one, I got to do a little bit more work before I get there. Okay. Since I don't have an isosceles triangle, but what I can do is take a mirror image of this triangle and put it on the other side. And this will help me get my sides. What kind of triangle, what kind of big triangle did I just create by putting a mirror image on the other side? It's equilateral, right? I've got a 60, 60, 60 all the way around, right? So the length of this bottom is 2. So the length of this side over here is 2. I created an equilateral triangle, right? So I know that it has the same length as what the bottom did. And now can we figure out this one here? Yeah, Pythagorean theorem again. Shocking. All right. Pythagorean theorem here would give me square root of 3. All right. So now we can use, let me erase that little arrow I stuck on there. Now we can use the two triangles to help us fill out the table, because now we know how to do each of the ratios. Okay. All right, so let's see if we can fill out this table. Notice that I wrote the triangles of degrees. We want to start making sure that we are comfortable with our radians, because again, going forward, we do more things in radians than we will in degrees. One bigger reason for that is calculus works a lot better in radians than it does in degrees. All right. So 30 degrees is the same thing as pi over 6. 45 is the same thing as pi over 4. 60 is the same thing as pi over 3. Usually, if I'm thinking about how a way to remember that quickly when you start, I know that 180 is the same thing as pi. So dividing that by 3 gives me that one. Dividing that in half gives me that one. So at least you can get those two relatively quickly, I think. This one's just dividing your 180 by 4. Like I said, you want to get comfortable with these as we go forward, because we'll be doing a lot more with radians than we will with degrees, unless we're doing application type problems, and then they're usually discussed in degrees. That does get a little bit tricky, of course, if you're doing things and you're asked for approximating values. You'll have to make sure your calculator is in the correct mode if you're typing things in. Anyway, let's go through this now. So let's fill out the first row to start with. Let's just do 30 degrees across. Okay. Going back up to my triangle, if I want sine of 30, I want to look at this angle up here, right? If I want sine of 30, I need to look at that angle at the top. What do you get for sine of 30 degrees? Yeah, 1 over 2, right? A half there. Okay. Opposite over hypotenuse there. Okay. Doing cosine. Yep, square root of 3 over 2, right? Adjacent over hypotenuse. And then tangent will be 1 over square root of 3. Good. Sometimes you will see that rationalized as root 3 over 3. Again, I don't care if you rationalize it, but sometimes you'll see it that way. Especially when we do the 45s here in a second. But 1 over root 3 is perfectly fine with me. All right, the other ones now we should be able to do either by looking at the right triangle or remembering those reciprocal relationships, right? For tangent, the reciprocal of tangent is the cotangent, right? And that'll give us root 3. And again, we can check that as adjacent over opposite, right? What's secant going to be? 2 over root 3. That's the reciprocal of cosine. And then finally, cosecant will be 2. You will be expected to know these exact values. Now, good news is that you really only need to know the sine and the cosine. Talk a little bit about why we only have to know sine and cosine to go forward. But you really only have to remember sine and cosine. The other ones you can always figure out. That okay? We'll do the 45 here in a second, but I want to skip over to the 60. And I'm going to redraw the triangle down so I don't have to keep scrolling back and forth. I guess my triangle is written the other way around, didn't I? So I can reference it here. So I don't have to scroll up and down for you every single time. What about sine of 60? Yeah, root 3 over 2. Because now this is the opposite side over here. Cosine of 60 is 1/2. Because that's the adjacent over the hypotenuse. Tangent is going to be root 3. Good, because it's root 3 over 1. And now that we have those, we can figure out the other ones by doing the reciprocals, right? For cotangent, we're going to get what? 1 over root 3. For secant, we'll get 2. And for cosecant, we'll get 2 over root 3. Good. Is this okay? All right. The reason why I wanted to do these two first and then do the 45 last is because I want you to notice something about the relationships of these particular functions. So again, up here, my angle would be 30 degrees. The 60 and the 30 add together to give me 90, make up a right triangle. What kind of angles do we call those if they add up to 90 degrees? You remember from geometry what we call those? There's a name for adding up to 90, and there's a name for adding up to 180. For 90, it's complementary. Good. For 180, it's supplementary, right? These are complementary angles. What's the first two letters of the word complementary? Co. Complement, sine, cosine. Complement, sine, and cosine. Complement, tangent and cotangent. Complement, secant, cosecant. That's where the co comes from in those words, by the way. The sine of an angle is the cosine of its complement. The tangent of an angle is the cotangent of its complement, so on down the line. That's why we refer to those as the co-functions. Okay. The co comes from complementary. So notice that actually helps you a little bit for memorizing some values, right? If I know the values for 30, I flip them to get the values for 60. Right? Makes it a little bit easier. One of the things I like about math is that, there's some of the stuff to memorize, but there's not as much to memorize as you think. Usually other stuff you can derive it. All right. Let's do the 45. I'll redraw the triangle down here again so I don't have to scroll. 45, 45, 90, 1, 1, root 2. Sine of 45, 1 over root 2. Sometimes you will see that rationalized as square root of 2 over 2. I will write it down. Again, I don't personally care if it's rationalized at all. 1 over root 2 is fine. I've not played around with WebAssign enough to know that if you had to type in a value, if you leave it as 1 over root 2, if it's going to get mad at you. But 1 over root 2 is perfectly acceptable. What about cosine? Also 1 over root 2, right? We're doing an isosceles triangle, so the opposite and adjacent are the same. What's tangent? 1. And now again, that we know sine, cosine, and tangent, we can figure out the other three. Cotangent is 1, secant is root 2, and so is cosecant. Yeah, root 2. Good. Notice that we filled in the last 3 columns knowing the first 3 columns, right? You didn't have to think about it every single time. We could have also filled in the 3rd column using sine and cosine, right? We go back up to my definitions here. My sine is opposite over hypotenuse. My cosine is adjacent over hypotenuse. If I divide those two, your hypotenuses will cancel out. What do you end up with? Opposite over adjacent. Right? So you can figure out the tangent by dividing sine and cosine. All right. So actually, I want to summarize these properties in this one here. So we have different types of identities. So identities are different, so to speak, than other types of equations that you've dealt with before. Usually, when you're in an algebra class and you're given an equation, you're looking for x's that satisfy the equation, right? But not every x satisfies the equation. You're looking for the ones that do. An identity is an equation that is, no matter what you plug in for the variable, it's always true. It is a true statement no matter what you plug in, as long as what you plug in is defined. Make that little caveat at the end. Okay. Right. So some of the identities that we have in trig have special names. So we have these first few here that we're able to write down based on what we just did. So we have the reciprocal identities. We've already noticed those, right? We had sine, cosine, and tangent. Oops. Which function is the reciprocal of sine? The cosecant, right? Or I could write it the other way around as well. Oops. These are what we mean by the reciprocal identities. Right? So sine is the same thing as the reciprocal of cosecant and vice versa. This is what I meant by as long as I don't have any issues plugging the number in, by the way. Notice that when I start doing reciprocals, I can divide by something that's 0. We haven't seen that yet, but we can. So I don't worry about it if it's undefined. I'm only worried about when it's defined. Reciprocal of cosine is secant. So again, that gives me a couple of other reciprocal identities. And reciprocal of tangent is cotangent. Good. Those 6 are what we mean by the reciprocal identities. Those are true statements, no matter what you plug in for theta, as long as you don't end up with an undefined statement. Okay? All right. Ratio identities, that was one I just mentioned a minute ago. We said that tangent is the same thing as sine over cosine. Because again, if I take those ratios and I divide the sine by the cosine, the hypotenuse will cancel out. And we end up with opposite over adjacent. The other ratio identity that we're interested in is for cotangent. If tangent is sine over cosine, then what's cotangent? Cosine over sine, good. Those are the 2 ratio identities that we're talking about that we have. And we've already talked about them a little bit, so we're just kind of tying it up as we go here. We're going to have a lot of other identities as we go forward. But these are kind of the basic ones that you will use, pardon me, over and over and over again throughout lots of math. All right. The last ones we talk about are the Pythagorean identities. We call them Pythagorean identities because they come right directly out of the right triangles and using the Pythagorean formula, or theorem, sorry. Okay. So, using the notation that I had before, you don't have to rewrite this, but I'm just, this is my theta. Using our notation that we had before, I've got an angle here, opposite, adjacent, hypotenuse for my sides. Okay? Pythagorean theorem says opposite squared plus adjacent squared equals hypotenuse squared, right? Agreed? Okay. Divide everything by the hypotenuse squared. I end up with a fraction that looks like opposite over hypotenuse squared plus adjacent over hypotenuse squared equals 1. Right? If I divide both sides by hypotenuse squared. You agree with that? Got a better name for opposite over hypotenuse? Sine. Got a better name for adjacent over hypotenuse? Cosine, yeah. So this becomes sine of theta squared plus cosine of theta squared equals 1. This is not typically how we write those functions, by the way, but this is what they mean. So sine of theta quantity squared plus cosine of theta quantity squared equals 1. That's what's one of our Pythagorean identities. But we write this in a shortcut manner, so we don't have to write parentheses all the time. Okay? So a shortcut way to write this is we put the square on the function name. And a lot of times we say sine squared theta plus cosine squared theta equals 1 because we're just reading it from left to right. But don't get confused by the notation. This notation means you're actually doing this. You're taking the sine of the angle and then squaring it. You're taking the cosine of the angle and then squaring it. Okay? It's really funky, right? This all by itself means that you did something bad twice. Or you did something twice as bad. Still says sin, right? Okay. It really does mean take the sine of the angle and then square it. Even though it's written kind of funky. This is one of your Pythagorean identities. We can get the other two by doing dividing both sides by sine squared of theta, or dividing both sides by cosine squared of theta, and simplifying. If I divide both sides by sine squared, what does this first one come up as? If I divide both sides by sine squared, what does this become? 1. What does this one become? Cotangent squared. This one becomes 1 over sine squared would give you 1 over sine is the same thing as cosecant, so you get cosecant squared, right? So another Pythagorean identity is 1 plus cotangent squared equals cosecant squared. Rather than dividing both sides by sine, divide both sides by cosine. If I divide both sides by cosine squared, sorry. If I divide by cosine squared, what does the first term here become? If I divide it by cosine squared, I'd have sine over cosine squared is tangent squared, right? This one becomes cosine squared over cosine squared will be 1. 1 over cosine squared becomes secant squared. So the other Pythagorean identity is tangent squared theta plus 1 equals secant squared theta. I want to go back to that picture that I drew at the beginning to tell you where some of the names of these functions came from. I said if I had a radius of 1 and we had that side and this was the angle, this was tangent of theta and secant of theta. Do you see the Pythagorean theorem there? 1 plus tangent squared equals secant squared, right? Agreed? Okay. You can also do, let me draw a different picture. Oops, this way. This is my theta, but let me go this way. Let me do a different triangle. If this is theta in here, this whole thing is what right here? That'd be 90, right? So this would be 90 minus theta. But this is tangent again, this is theta up here, isn't it? Right. Okay. Notice that this triangle here would look a lot like this one does, right? Except my theta is in a different spot. Turns out that this side, doing this way, is your cotangent of theta. And this side would be your cosecant. Did I do that right? I may have messed that up a little bit. Anyway, you can get the cotangent of theta by looking at the other side. Looking at the other, I may have messed up my picture a little bit. But you can get your cotangent by drawing the other picture, is the idea. Oh, that's what I need to do. I want to do, let's not do it that way. Let's make this the complement. Oops. And this my theta, and now that's cotangent. Anyway, doesn't matter. That's the same idea. The last one from a picture's perspective is more important anyway. I just was trying to give you an idea of where the names come from. If this is my theta, and this is 1, if I drop the perpendicular down this way, this side is still 1 because that's a radius of the circle, right? So this side is your sine, and this little side here is your cosine from the triangle or from the circle. That is something that is helpful for us later on, looking at a circle from that perspective. All right. Let's see if we can use some of our knowledge now of trig to help us do what they refer to as solve the triangle. And then we'll do some application problems next time. When you are asked to solve a triangle, there are 6 pieces of information associated with any triangle that you come across. There are 3 angles and 3 sides. So when it says solve the triangle, it means find the missing information of the 6. Right? Now, everything that we're doing in this section is a right triangle. So really, we're given 3 pieces of information. We're given that's 90 degrees, right? Okay. So in this case, we're being asked to find 1 angle and 2 sides. Well, the angle shouldn't be too bad, because what does the 28 and this angle have to add up to? 90, right? So our measure here of angle B has to be 90 minus 28, which is what, 62? Yeah, that's not too bad, right? Okay. The other ones, well, once we figure out one side, we could figure out the other one using Pythagorean theorem. I want to figure them out using trig functions just because I want to practice with that a little bit. If I wanted to find A, what trig function do you think you might use to help? Just looking at this particular picture, what trig function do you think you might use to find A? Sine, because I'm given this angle and I'm given the hypotenuse and I want the opposite side, right? I have 2 pieces of information and I want to figure out the third. So what equation can we set up here? Good. Sine of 28 equals A over 16.2. To solve for your A, we'd have that. This type of problem would probably ask you to go ahead and get a decimal approximation. Make sure your calculator is in degrees for this type of problem, since it has 28 degrees. If you need help changing your calculator from degrees to radians and back and forth, let me know. On the 83s, 84s, it's under the mode, and you should see a radian and degree option. Okay. What did you get for that particular length? 7.61? Good. One thing I can tell you for certain is that if I'm finding the length of this side, it better be less than the hypotenuse. So the hypotenuse has to be the biggest side. It also can't be negative, right? Because I'm finding the distance here. If your calculator spit out a negative number, probably means you're in radians rather than degrees. All right. What other equation can we set up to help us with B? Let's use a trig function. I know we can do Pythagorean theorem, but let's use a trig function. What trig function could you use to solve for B? Good. Cosine of 28 equals B over 16.2. So multiply both sides by the 16.2 again. And what did you get there? 14.3 is what you said? Okay. Your problems in WebAssign will tell you what decimal place to round to. I think this is probably good to 2 decimal places, from what I heard. The reason why it's better to go back to your trig function here rather than using the Pythagorean theorem is you rounded to get this one, and then you would round again to your hypotenuse, or sorry, the other leg of your triangle. And it's going to cause compound rounding errors. So always go back to your given values if you can to compute new ones, and then I'll minimize around here. All right, so we don't have class Monday, of course, for Labor Day. I do want to do a short quiz on Wednesday over the first, not this stuff, the first section, the angle stuff. Okay. I'll do that at the end of class, so that when you're done, you can leave. So we'll work on these application problems that are at the end of this packet on Monday, and we'll do a quiz at the end of the hour. Excuse me, not Monday. Just so we don't have class on Monday, Wednesday, and then we'll do a quiz at the end of the hour.
On the other side, like you get put something in and you don't like certify out or something, but it's still technically right and it's wrong. You like go in and like check it.
Yeah, or you could, if you get something like that and think it's right, shoot me a screenshot.
Okay.
Right away when we do it. That way you're not guessing whether or not. Yeah, just shoot me a screenshot of it if you got a question about it.
No, it's kind of funny because yesterday I did the website stuff and I put in the answer. I just put it in the wrong word again. It was asking to like I can't pronounce it, the continental.
Oh, yeah.
Yeah. And I put it in right, then I put it in a different order,
And
and then it worked. So
Oh.
I'm like, okay, sure.
Oh, sure. Why not? Oh, yeah, the co-terminal ones, yeah.
I had a question.
Yeah.
6.1.
Yeah.
Same thing we did both this. Can you post like the answers that you wanted to check that?
The ones that we didn't do? Is that what you're asking me? The problems from the notes that we didn't